Talk about derivatives and tangent lines of parametric curves. At the top of the page here, you can see our most important formula for this. dy dx, which would be the slope of the tangent line to the curve, is the ratio of dy dt over dx dt, or if you'd like it in prime notation, that's y prime over x prime. Okay, so I have two problems ready for this video. The first one you can see here with a part A and part B. So this is our parametric curve here. X is 2 sine of t, y is 4 cosine t. And we're asked first to find a formula for dy dx as a function of time. So dy dx, we're going to use exactly the formula in red up here. We have y prime over x prime. The derivative of the y function is 4 times negative sine. And the derivative of the x function is 2 times cosine. We could leave it here, or we could simplify it a little bit. And that's our answer for part A. So essentially what we have here is a formula where you would plug in any given time value and compute the slope of the tangent line from this formula. Okay, so we're going to use this to answer part B, which asks us to find the equation of the whole tangent line to this same curve at this time value pi over 4. So to get the slope of our tangent line, we're going to plug pi over 4 into this dy dx. So we have negative 2 sine of pi over 4 over cosine pi over 4. Sine of pi over 4 is root 2 over 2. Cosine is the same, so these actually cancel. And we get negative 2. This is the slope of our tangent line. This is the m. And now we need just the xy point. So what's interesting here is that we were given just a time value to indicate the tangent line moment, which was convenient for dy dx, but it doesn't explicitly tell us the xy point. So we actually have to plug this t value into x and y here to find the xy point at this time. So x would be 2 sine pi over 4. So that's 2 times root 2 over 2, so that's positive root 2. Y is 4, cosine pi over 4, which is 4 times root 2 over 2, which is 2 times root 2. All right, so the xy point is root 2 comma 2 root 2, and the slope is negative 2. So we need a line equation that has these properties. So I'll say y minus 2 root 2 equals negative 2x minus root 2. This is the point slope form of the equation. If you want, you could distribute this negative 2 and swing the 2 root 2 over to get point slope, or slope intercept rather. All right, but I'm going to leave this answer here. This is my final answer for part B. Okay, so the last example for this video will be the following. Find the equation of the tangent line to this new parametric curve at the point negative 3, 1. So if we compare this to what we just answered, it's still a tangent line for a parametric curve, but this one gave us the time. This one gives us the xy point. So we won't have to do this part here because we already have the x and y. But what we don't have is the t value that creates this point. So instead of this, we'll have to backtrack to find the t value. Why don't we do that now? So if x equals negative 3 and y equals 1, what is the time t? So I know that the formula for x is t squared minus 4. And the formula for y is root t. So what I might do first, typically I just kind of take the x formula and solve it for t. That's not the most efficient thing here, but it's what I'm going to do to make a point. I want to solve negative 3 equals t squared minus 4. So I will add the 4 over, plus or minus square root both sides. And I get that t would be either positive 1 or negative 1 to create this x value. Right? So then we bring it to y and say, all right, which, if any, of these t-values makes y +1. And we can see from this formula here, t would have to be +1 since we can't square root -1. So t equals 1 is the actual time value that's going to create this point. Okay, so now we can do dy dx for the slope. This is going to be y prime over x prime. And now we're plugging in t equals 1. And we get 1/4 for the slope. So we have this point, this slope, and we can go straight to our line equation and stop there.